Assalamu alaikum and good day. Today we try to cover the last chapter which we didn't manage to finish before the lockdown. So it's on powder mixing and segregation. Basically, mixing and segregation is a topic that you cover together because if you understand segregation, you should understand how to uh, make a better mixture. All right. Well, the aim of this chapter is to let us understand the behavior of particulate during mixing. Is it spending more time in mixing a powder will make a better mixing or otherwise? So it is important first to achieve what we call a good mixing, what we want in a mixture, and we have to understand all the physical properties of powder which contribute to mixing and also contribute to unmix. Yeah? So mixing and unmix is a topic that we discuss together. So unmix basically means segregation. So we have mentioned and emphasized again and again that different in particle size contribute a lot to the process of segregation. So we have make assumption, make analogy that powder basically behave like human being, so they tend to choose uh, powder with the same characteristic to group in one section and leave the others as just like human being, where we choose people who tend to speak the same language with us, practice the same culture, and have the same hobby with us together. So basically, the main issue that we want to talk about is about particle size, different in particle size, which contribute to segregation, and all the other characteristic of powder like density, shape, uh, and whatnot. Basically, they are not that important. The most important issue is particle size. So bigger size, we know they contribute to free flowing, and when particles have the freedom, just like human beings, they tend to choose to be among themselves, which means they tend to be segregated. Okay, so in order to avoid segregation, which is a process to unmix a powder, we have to avoid all these processes during a mixing process, which is like pouring, tumbling, and vibrating. Yeah, so we should not use all this process in a mixing process, and because we want to achieve a mixture which is what we call random mixture. All right, so but then we know that to in order to mix a powder we need some kind of tumbling, some kind of vibration to let the powder move around, to choose their position where they want to be. But then also bear in mind that all these freedom that we are giving to the powder actually can also promote segregation. Okay, so in the chemical industry, most of the time we mix powder. We need to put powder together, and normally we make multiple component mixture. But to make things easier for us to understand for this topic, we will start with binary mixture. So we are mixing only two powders, two different powder together. So in the chemical industry, it is very common for us to do mixture like in the food industry, in the pharmaceutical industry, and in any industry, we have all sort of solid mixing equipment which is available for powder mixing. And we want to know what is meant by adequate mixture. How do we know that we have achieved the mixing that we want? How do we measure them? What kind of criteria we use to measure adequate mixture? And we also want to know what happened during the mixing operation, what actually transpire. Are we actually mixing them or we are unmixing them? So we want to see what happened inside. And of course, as I mentioned earlier, we want to know all the physical properties, how they contribute to mix a powder. Yeah? And, uh, and therefore we need to know when is the correct time that we know that a satisfactory mixture has been completed. So in a powder mixing process, normally we use equipment and we want to know what kind of design features in a powder mixing process, the equipment, what are we having, and the acceptable standard for the performance. How do we measure? What kind of number, what kind of index are we using to measure solid mixing that we know that we have achieved to the standard? Before we talk about the mixing process, let's try to understand what kind of mixture that we are trying to achieve and what kind of mixture we are trying to avoid. Yeah? And in industry, normally when we mix powder, we are mixing powder of different physical properties, especially different in size, and there could be also different in density, in hardness, in all sort of physical properties that could be different. And we want to understand what actually contribute to unmix or segregate, and this topic should be discussed together with powder mixing. So this is something that what the theory that we want, which is an ideal mixture, which we know that we cannot even approach, we cannot even get near to this ideal mixture. Ideal mixture is that if I were to mix white and black powder together, 50% of white and 50% of black, and I should want that at the end of a mixing process, I have one white powder, and the next to that white powder should be a black, and next to the black should be a white, and the arrangement is such that it is perfect. So this is something that we cannot achieve. This only happen in theory. We know that when we are dealing with powder, we are dealing with millions of particles. It's not possible to sit down and arrange particle one by one that this after this color should come the next color and so forth and so forth. So this is something which is not even get near to, yeah? And so we don't dream about this kind of mixture. So the best that we can aim for is random mixture, or is what we call random mixture. Random mixture is the probability of finding particulate in a given component at any point the mixture is equally proportion at the whole mixture. What is mean by that is that when you take sample from a mixture, you will not get exactly the same composition, but you are getting a very close case of variation, and the variation should be very, very small. So random mixing is that if I were to mix white and black powder together, so if I sample from the top, or I sample from the middle, or I sample from the bottom, I should get more or less the same composition. Not exactly, but then more or less the same. If I were to mix white and black powder together, so I want 50-50, 50% of white and 50% of black. So if I were to sample 6 particles from the top, or 6 particles from the middle, or 6 particles from the bottom, I should get very close to 50-50. Maybe 45-55, maybe 48-52, and something like that. So this is what we call random mixture. So random mixture is what we are aiming for in an actual powder mixing process. In an actual powder mixing process, our aim is random mixture, not perfect mixture as the one that we talked about just now. So this is what we hope for. So segregated mixture is that you will find that after the process of mixing, you will find most of the black powder actually sitting at the bottom and most of the white powder sitting at the top. So you won't find a 50-50%. So at the top, you will have more white powder compared to the black, and at the bottom, you will have more black powder compared to the white. This is actually a segregated mixture, which is not something that we want. So our aim is random mixture, and of course we want ideal mixture, which is not achievable. And at the same time, we try as much as possible to avoid random, what I call segregated mixture. Okay, having understand what is powder mixing and what is the end result, which is the powder mixture that we get. Now we try to recap and look into the whole issue again. And we know that powder mixing is more of an art than science. So we have made many analogies about powder, and most of the time we are trying to say that powder behaving like human being, and so we should understand from that angle rather than so much based on science. And please do not use liquid mixing or gas mixing in comparison to powder mixing. In liquid mixing, it's easy to achieve the perfect mixture that we want just by simply putting the liquid into a container and put a stirrer and stir for some time. The the mixture will be homogeneous at the end of the process, and we should be happy with the mixture. But then for powder mixing, once we achieve our complete mixture, we can only aim for random. Yeah? We aim for random mixture, but not a perfect mixture. So the question is, how do we measure that? How do we know that we have reached a degree of homogeneity uh, in a powder mixture? And to understand this, we need to know what sample size to take, or what we call scale of scrutiny. So when we started to mix powder, if I were to put in black particle and white particle, so at the initial stage, they are totally segregated. Yeah? If I were to introduce a stirrer into the container and let it mix for some time, after some time, I could get something like this, yeah? Which is what we call the random mixture. We know that in theory is not possible. In theory, we would like to have something like this, which is a perfect mixture, which is one black, one white, one black, and one white. But this is not achievable. So the best that we can aim for is what we call the random mixture. But then another question arises from here is that how do we know uh, that the mixture that we have been trying to mix have achieved to the homogeneity that we want? So there's the definition of scale of scrutiny. What is the scale of scrutiny? Yeah? So each user will have different scale of scrutiny. So if you are looking at this screen at this moment, if we take a small portion of the screen and we try to analyze, uh, the whole screen is actually look very nice. But then if we take a small portion of the screen and we try to analyze the screen, then we see that the pixel actually is not that nice. They are not that clear and so forth and so forth. It depends whether the person is actually looking at the whole screen or they are looking at a portion of the screen. So that's what we call scale of scrutiny. Remember, I was talking about mixing of animal food, like for chicken. Yeah? When you mix drug with chicken food, for a chicken, the scale of scrutiny is actually down to the milligram. Yeah? Because they can see things which is very small, and they can actually choose drug from the mixture of the food. So in this case, if we have a bigger scale of scrutiny, we might be happy with the mixture. So if our scale of scrutiny is getting smaller and smaller, then our satisfaction might be different depending on who is our end user. Yeah? So for people in the pharmaceutical industry, the scale of scrutiny will be different. For people in the display industry, like for TV screen and so forth, the scale of scrutiny are different. For people who are making food for cow and for dog and so forth, so the scale of scrutiny are different. So when we talk about complete random mixture, is again not only depending on the mixture but it also depends on the scale of scrutiny. So why does segregation happen? Segregation happens because of different physical properties of powder. If I'm mixing two powder together, if these two powder having the same size, same density and shape, I should have no problem in achieving a random mixture. It should be all right. eh? But in real world, we know that there is no such thing that people are mixing powder of the same property, exactly the same properties. There will be somehow some kind of different in properties for powder mixing. Most of the time, we are mixing powder of small size with a big size, and maybe different density and so forth and so forth. So, from all these physical properties, the main culprit is the particle size. If I'm mixing a powder with a size ratio different huge, so I should prepare to face the problem of segregation. eh? So size by far is the main culprit in segregation. So in powder mixing, most of the time we have different in particle size, different in density, shape, resilience, hardness, and so forth, composition, and so forth, and so forth. Okay. So if I have a segregated mixture, it will have impact on the packing, which will give me a different density, a different bulk density, because I will not get the same weight for the same volume because of segregation. And of course, the main issue is quality. Quality is that normally when we mix powder, we want to mix the active ingredient with the filler, or what we call the carrier. Yeah? So we want a certain percentage between the active ingredient and the filler. So normally if we design a drug, maybe 20% drug and 80% filler. So if we want that, so the quality could be compromised if segregation already occur. Okay, now let's look at when will segregation happen and how does it happen. Segregation happens basically due to four factors, four mechanisms where segregation can happen. The first one is what we call trajectory segregation. Trajectory segregation is normally happen when we provide freedom to the powder. When we pour the powder from a container onto a surface, a dumping powder from a lorry carrying powder sand maybe on the floor. So when we do the pouring process, basically the large particle will have a tendency to fly further. So the big particle will have a tendency to go further compared to the fine particle, which will have a tendency or less momentum to fly further. So at the end of the process, you will see a cone on the floor, and you will see mostly from the outside, the big particle will be sitting at the outside, and the fine particle will be sitting at the inside. So this is mostly due to size. uh, Based on the equation of tragic, you can see uh, in the drag coefficient equation, the bigger the size of a powder, the further the powder will move away from the center. So this is one form of segregation that we can avoid, which is the pouring process, the process where the powder actually being given freedom to choose the location where they want to be. The next process that can promote segregation is what we call percolation. Percolation is the process of fine particles pushing their way to move to the bottom. So you can imagine that this happened during rush hour where everybody rushing to get into the LRT or whatever public transport. So you will find that most of the small ladies with a sharp elbow, they will be able to push their way in a crowd to the front to get themselves into the transport. So the same thing happen in a container. If you have a good mixture of particle, And once you are given them freedom, either in the form of vibration or shaking, just like those good mixture which you already mix it well in the plant, and you transport them. So during the process of transportation from the plant to the supermarket, so the powder will have a chance to go through this vibration, the bumps on the road and so forth, and they will use their sharp elbow. Because of their small size, they could actually reach to the bottom of a mixture. So this is also a way of promoting segregation. And the third way in which segregation happen is what we call rise of the big particle to the top. Yeah? So this is again in the process of transport. It happens during the process of transportation, where the fine particle penetrate to the bottom and the big particle actually moving up to the top, yeah? Giving space to the particle at the bottom, and in the process of giving space to the particle at the bottom, the big particle tend to move up by itself. And the last mechanism in which segregation happen is what we call elutration. Elutration is a process normally happen in fluidization. When you fluidize a powder, you are lifting the powder using some kind of gas from the bottom. So normally it's much easier to lift the fine powder because they are much lighter compared to the big particle. So in this process, you could also blow the particle out from the container. If you are not able to blow them out, so they will stay at the top and the big particle will be at the bottom. So this process is what we call elutration. Yeah? So normally this happen in a fluidized bed when you use a fluidized bed for powder mixing. Summarize the mechanism for segregation. Basically, there are four. The first one is due to trajectory, which is pouring. Second one, what we call percolation, which we talk about the small lady with a sharp elbow. Yeah? And also the third one is due to big particle, the coarse particle, moving up to the top due to vibration. And the fourth one is mostly due to fluidization, where the fine particle tend to segregate themselves to the top by the process what we call elutration. Well, once you understand what actually promotes segregation, now we want to talk about what actually can promote a good mixture. So, first thing we want to highlight two process which can actually promote good mixture. We know that segregation happen when the particle size difference between the two mixture that we want to mix are huge. So, if possible, try to mix fine powder. So when we talk about fine powder, we are talking about powder which is less than 45 micron. In terms of mixing, we are talking about powder less than 10 micron. So we mentioned in the very first lecture in this subject that for particles which are very fine, the van der Waals forces, or what we call the interparticle forces, are normally very strong. So they will hold on to each other. So with that, we have a very cohesive powder. So with that, it is much easier to achieve a random mixture. So with particle size getting smaller, the interparticle forces getting stronger. So when they have interparticle forces which are stronger, so they have less freedom. So with less freedom, they will have less opportunity to segregate. Number two, what can we do is to add a small amount of liquid to prevent the powder from having freedom. So we know that now our main enemy in mixing is actually freedom. Instead of giving them so much freedom to choose where they want to be in a container, so we'll try to limit their choice by adding small amount of liquid, and with this small amount of liquid, so it should act as a bridge between two different particles. So this bridge will actually promote better mixing by uh, sticking the particle to another particle. So the amount of liquid actually is used to stick particle on the other particle. So that will give them less opportunity to choose where they want to be on their. Well, so to reduce segregation, if we can summarize, there are five of them. First is to make the mixture, the two particles that we want to mix together by having more or less the similar size. How do we do that? So of course, this is by what we call grinding. So you grind the powder to more or less the same size. So when they have size different which are very small, so the possibility of segregation will be reduced. Yeah? And the second part of it is to reduce the absolute size. If possible, we do not want to mix free flowing powder, which is group A powder. We want to mix powder with higher interparticle forces. So we try to mix powder which are in group C. Yeah? So if possible, all of them are less than 45 micron. And if possible, make it smaller, less than 30 micron. And the third one is the one that we mentioned just now, which is by adding a small quantity of liquid into the mixture so that we stick the big particle to the small particle together in a surface, which is what we mentioned in point number 4, which is to something like coating. Yeah? So you coat the small particle on the surface of a big particle. Yeah? So number 3 is adding liquid, so we don't do coating. Number 4 is more like a coating process where you actually stick the small particle to the big particle. And number 5, if you can't do anything from the 4 that we mentioned above, then you should avoid anything which promotes segregation. So what is the process that can promote segregation is the one which we talked about just now, which is freedom. Don't give powder freedom. It's just like pouring, like going down a slope, like vibration, shaking, and so forth and so forth. If we cannot do anything of the 4 that we mentioned at the top, then make sure that your process is actually do not have anything which promotes segregation. Okay, having understand how to promote a good mixture in a mixing process, now we want to look at some of the equipment which is available in the industry for powder mixing. And in all this equipment, you have these three elements. One of either of these three elements, which is convective mixing, diffusive mixing, and shear mixing. What do you mean by that? Basically, convective mixing is almost like a turbulent flow in a fluid. Yeah? So where you see the bulk movement of powder around the powder mass. So it's almost like a turbulent situation where we say Reynolds number above certain number, you get this kind of movement. Diffusive is more or less like diffusive in a liquid or gas. If you put gas in one corner, you will see that slowly the gas will be diffused to other section of the container. So this is more or less like rolling down from a surface, and shearing process is more of a process of flow which is analog. It is we say more or less like a liquid in a laminar flow section. So we have a mixing process more or less like a flow in a liquid. All right. So convective, normally we prefer this because diffusive and shearing, they are more tend to promote segregation because their movement is more like laminar and also diffusion. So, but then in commercial mixture, what is available commercially, we will see that people are trying to combine any of these process together so that in the process you will get uh, different type of test. So in convective mixing process, you will see that slowly from a completely mixture, you will get to a bulk movement of particle still segregated and slowly reaching to the random mixture. And in diffusion, you see it's more slower, the particle moving slower, and at the end, we still achieve to the random mixture that we want. All right. In the industry, we will see that there are many types of mixture which is available. Some of them where we see that actually the container actually move. eh? So the powder put into a container and the whole container actually moving. And in some industry where the container rotate, where the powder, the mixer actually rotate, but then the container didn't move. You have a ribbon inside or you have a mixer inside. And in some, you have both mechanism where the container move and also the content also move. And sometimes you even put in some buffers, plate to help to let the powder move. So all these process that we are talking about, all these processes that we are talking about, basically we are providing powder with the freedom. eh? But then initially when we discuss about this topic, we are saying that in order to avoid segregation, we must stop or providing freedom to the powder. But then now we are talking about giving freedom to the powder. So we have to give freedom to the powder initially to let them move and to let them mix around. And after they reach the random mixture composition, then we should not promote freedom anymore. So in the industry, you see all these mixture which is provided, which is available in the industry for us to use for power. So sometimes you see where the container actually staying stationary and the powder is being moved inside the container. Sometimes we use ribbon, we use screw mixer, tumbling process and black well. So mostly these the container are not moving and the powder will be moved by the ribbon, by the screw and so forth and so forth. So actually in your textbook, so I will not go into details on this where you see the powder moving radially across the container and also actually in a container, either through tumbling process or okay. So these are some of the equipment you see in the industry, V-shaped mixer, and these are mostly where the container is actually moving. And okay, so how do we know when to stop? So the rate of the mixing process is given by a number. So that number, how will it fare? So we know that with time, initially, if we are completely segregated, as time passes by, it should be getting better and better. But spending more time doesn't necessarily mean you get a more better mixture. So when you provide more freedom after you achieve the random mixture, your quality can actually drop after that. So spending more time means giving more freedom and spending more energy to mix the powder could actually help to unmix the powder. Okay, so these are all the mixer which is available in the industry. Uh, those I have mentioned. Those like the ribbon, where initially you have completely segregated, slowly moving to a better mixture up till you come to a random mixture. Yeah? Of course, with the scale of scrutiny that we were talking about just now. So the last section of this lecture is talk about how do we know we have achieved to a mixture that meet the quality that we want. So the quality of a mixture is depending very much on the end user. So we mentioned that we should understand our end user very well before we define what is the quality that we want. So the word or the terms that we define for it is what we call scale of scrutiny. Yeah? So just like for example in the process of making powder detergent for washing machine, so if we were to mix 30% soap with 70% filler, so for the consumer point of view, either is it the first scoop or the last scoop from the box, it should give them the same wash. Yeah? So the first scoop should contain 30% of powder, 70% of filler, so is the last scoop. So we have to mix the mixture by taking sample according to the size of the spoon which is provided in the detergent box. Yeah? So for them, the scale of scrutiny is one scoop of powder. And for drug industry, we are talking about tablets. Yeah? So one tablet, the tablet, the composition in the tablet, if we are talking about 20% drug and 80% excipient or 80% filler, so each tablet should have more or less very close to 20-80 ratios. Yeah? So we are talking about it. So sampling is very important in in a powder mixture because this will tell you whether the mixture is it good or not good. So the sample size depend on the scale that we are talking about, which is scale of scrutiny. Again, this scale of scrutiny is defined by our end user. If I were to put the powder into a container, 20% of drug and 80% of excipient or filler. So if I take the whole container, of course, it's already well mixed. But I need to sample according to the size of my end user, how they define scale of scrutiny. Okay, so scale of scrutiny, what is that? Basically, is the maximum size of a mixture which can be considered as not perfectly mixed. So this scale of scrutiny is the number of particles in that mixture which is defined by the end user. Yeah? So we have to understand our end user one by one to define what is the scale of scrutiny. So this definition has been given by Danquat in 1953. Okay, so just to recap, what is scale of scrutiny? So for certain people, the scale of scrutiny could be bigger number of particles, but for certain people, the scale of scrutiny can be only 4 particles and so forth and so forth. So it is different depending on end user. So in terms of statistic, we are talking about how far we are away from the mean. Yeah? If I were to sample something to determine whether this mixture is good or not good, is to know whether the sample they have taken, how far is it from the mean. So the number that we use to define this difference is what we call standard deviation. Yeah? Standard deviation is the mean that we are hoping for and the mean that we measure. If we know the difference, power 2 divided by the scale of scrutiny. Yeah. So okay, so let's talk about mixing of two mixing of binary powder, two different powder together. So in the process of mixing, we are trying to give the analogy of mixing of a powder just like running in a marathon. Running in a marathon, you have two limits, the upper limit and the lower limit. So when you started running in a marathon, basically you are at the upper limit. Yeah? Upper limit means you have completed 0 kilometer. You have not started yet, the mixture is completely segregated. You put in powder A and powder B later. So they are not mixed, they are completely segregated. By the time you finish, which is what we aim for, when you finish, we have a random mixture. So you have actually completed your 10 kilometer. So you are running from 0 kilometer to 10 kilometer. So when we started running, if I were to put an analogy to powder mixing, so it will be powder A and B. So powder A, if I put in 1 kg of powder A and maybe 3 kg of powder B, so 1 kg and 3 kg. So this, if I were to mix them together, it will be 25% and 75%. So 1 kg out of 4 kg is 25%. This is 3 kg out of 4 kg is 75%. So it's 0.25 times 0.75. So by the time I finish, I want the same composition. But when I want the same composition, I should look at it from the point of view of scale of scrutiny. So basically, N means the scale of scrutiny. So when I started, I want 0.25 times 0.75. When I finish, also 0.25 times 0.75, but in the viewpoint of scale of scrutiny. So N is the scale of scrutiny. So from here, so from there, we come up with a mixing index. Mixing index is what we call the lazy mixing index because this is the index introduced by lazy and is the starting point to the end point. So when I start, I know what is my standard deviation. When I stop, I should know the standard deviation based on scale of scrutiny. So when I started and when I sample from the powder compared to the one which I supposed to reach, so I should know how far have I run in a marathon. So the index to let us know whether we have achieved a good mixture or not is by referring to what we call the lazy index. Okay, so 0 means completely segregated. If I have reached 1, that means I have reached a completely random mixture that I want. So this is the equation for that. So normally in a mixture, we want something very close to 1, even though sometimes we cannot even reach 1. So we do not spend more time than this to go beyond that. So we are all right if we are somewhere in this region. Okay, so this is the index that has been used very popularly in the powder mixing industry for binary powder. And some people try to simplify by taking away the two thing at the front by giving this ratio. But this is not that popular in the industry. So we will more refer to this index rather than the other one. Okay, so then you can use the student test to see the confidence level where you are, and most of this example you can see in your textbook. So I will not go further on this or this section because we will be doing exercise in the next lecture on how to do calculation for the mixture and how to determine the time that we need to spend for producing a good mixture and and we should know that we shouldn't waste energy to go beyond the time when the mixing index is already going to the lower value. So our aim is to move from 0 to 1, which is 0 is the starting point in a marathon race, and we should reach to 1, which is all very close to 1 at the end of the mixing process. So to summarize, we have to emphasize again and again, powder mixing is something that you have to understand based on segregation process. And we also look at the equipment for mixing. So we prefer to use a convective mixing because this will promote more homogeneous mixture, and to know the quality of a mixture, either is it good or not good, we are using statistical method, which is a standard deviation, and we have to look at also one of the important factor in powder mixing, which is what we call scale of scrutiny. And scale of scrutiny is a different number depending on our end user. Yeah? How our end user using the end product, so that will determine the scale of scrutiny. All right, so with that, I think we complete the lecture today. And so the next one, we'll look at one example, how to do the exercise on calculating the lacy index to determine the mixing quality of a mixture. And the rest of the exercise, basically, you can actually look at your textbook on the chapter on powder mixing. Okay, thank you very much. Bye.